Hi, everybody. I have a cat here, so she might suddenly meow and you'll hear her. Not that that has ever stopped any lecture before. Now that I've introduced her, she has left, so never mind. We're doing chapter 4 today. Today is naming day. We're going to do all the nomenclature. Some updates for things that are due. Lab number 4 is due tonight. Make sure you get that in by the deadline. Really, just get it in by last call whenever I announce it tomorrow. And quiz number 3, quiz for chapter 3, I should say. It's actually a 4th quiz, is due next week on the 11th. The quiz for chapter 3 is very long. There are a lot of small questions. The best way to prepare for those is to know the material, really. But if you don't know 1 or 2 topics, like, they're all really worth 1 point each, so not a huge deal if you're like, crap, I don't remember exactly what this is, and I don't want to spend all this time on it, then. And again, you get 2 attempts, so you know. Alright, so chemical nomenclature is going to be the focus of today's lecture. We might get to Lewis symbology, that would be nice. But we have a lot of naming in our future. We need to start naming molecules because we can't just be calling them like Bob or Suzanne or, I don't know, like, I'm not good with names. I was going to start calling them things like Donovan or Jasmine or whatever characters from my novel that I'm writing, but we need to give a systematic set of rules so that we get the same outcome every time, and we don't have to memorize a bunch of just random names. For example, we call water, which is H2O, we just call it water, but that's not what it's called in, say, France or Spain. Like, it's called aqua there. And in other languages, it's all different. But if we had, like, a systematic set of rules that went past all languages, then, like, I could talk to a chemist in Russia, and that chemist in Russia, she could talk to a chemist in, like, South Africa, and then that chemist in South Africa could talk to somebody in Argentina, and they would all know what they were talking about without having to put it into Google Translate. And if anybody's put anything into Google Translate, you have definitely seen how good that is. So there's definitely an interest in having a consistent set of rules, and that set of rules that we've devised is called nomenclature. We're going to name 4 different types of compounds in this class. If you take a 140, you've probably seen all these rules, so this should be an easy day for you. If not, it is time to review. We're going to name binary ionic compounds. Binary ionic compounds are any ionic compound that has only 2 elements in it. So like potassium oxide or sodium nitride or something like that. We're not going to name combinations that have 3 or more elements in them because there's not really a defined, set of rules to do that. Though such compounds definitely exist. We're just not going to give names to them. Polyatomic ions are common enough that we have a naming scheme for them too. And it is very similar to that of naming binary ionic compounds, as long as you know what the polyatomic compound is, or ion. Binary molecular compounds are any sort of covalent molecule that only has 2 elements in it. And then acids have a special set of rules, and they always start with H+. So we'll talk about that in a little bit more detail when we get there. Alright, so we're going to start right off the bat with just naming ionic compounds. And this is the algorithm that you want. You want to be able to name the metal. And when I say name the metal, I literally mean, what is the metal's name? Go find it on the periodic table. Just drop it in the box. And then name the nonmetal with "ide" on the end. And so this little thing right here, we're going to talk about in a little bit more detail, because you've probably heard the suffix "ide", because I try and use it when it's appropriate, and sometimes I even misuse it because I just speak too fast. But we'll talk about what that means. Balancing equations, Pivnert, and oxidation is 162. Oxidation specifically is actually 163. When you are naming substances, and you are giving the name for your metal, you just go straight to the periodic table and take it right off of there. Now, there are some gimmicks for this that we have to be mindful of. So here are the gimmicks that we need to consider. First of all, if your element that you are taking off the periodic table is in column 1A, column 2A, or it's aluminum, The only metal name that you write down is just the element off the periodic table. So if you had sodium, you would literally write sodium, just like all these examples here. But if you have any other element, then what you need to do is indicate its charge. And the charge of that metal may be variable. The first group of elements up here, these guys up at the top, these are all what are known as fixed charges. And so the fixed charges are all the elements in groups 1A, 2A, and aluminum. There are actually extra ones, and I don't know if your textbook actually includes these. So the other ones that are included are gallium, which is always +3. Zinc and cadmium, which are always +2. And then silver, which is always +1. So for your purposes, when you're naming stuff, if you are naming any of the elements that I've indicated, group 1A, group 2A are aluminum, then you don't put a number on it. It's just proper not to. If you do put a number on there, Canvas won't recognize it for 1, and then other sciences will laugh at you for 2. For the ones that are over here that I've written on the side here, these 4, this will be optional. And if I use these elements, I will program in both names so that it will accept gallium or gallium-3, or zinc-2, or whatever. So I'll give you the option, just because some textbooks don't have these in them as fixed charges, and some textbooks do. And I forget what our textbook does because I haven't read it in, like, a year. So now, if you are any other metal on the periodic table besides the ones that are indicated above, let me get another color here. These are what we refer to as variable charged metals. And whenever you have variable charged metals, the number that you indicate right here is the charge written in Roman numerals. Now, this requires us to know our Roman numerals. So if you've never used Roman numerals before, you're going to do that now. So let's write out our Roman numerals. I don't know where that pen stroke came from. My pen wasn't even near the tablet. So the numbering system that we use is the Arabic numbering system, which is super awesome because it's base 10. And then we have the Roman numbering system, which is just dumb. Alright, so the Roman numbering system is sort of base 5 with extra fun bullshit thrown in. And the only things that you ever use the Roman numerals for are the Super Bowl, Final Fantasy, and naming ionic compounds. Those are the 3 things that we use Roman numerals for. They're completely worthless otherwise. So if you haven't seen them, now you can decipher those like codes at the end of TV shows where they say like MMMMMCMXI or whatever. That's what's going on here. So 1 is an I, 2 is II, 3 is III, 4 is IV, 5 is V, 6 is VI, 7 is VII, 8 is VIII, 9 is IX, I'm kind of running out of space here, and then 10 is X. And I don't even want to touch the name of Elon Musk's baby, because that is just like... That poor child. There are some adults that should not be allowed around children. And if you name your child a string of characters like that, I can't type it. I don't even know how to say it. It's like XA and then the schwa symbol or whatever. I don't know what the AE smushed together is. And then, like, I know the last few letters are like a jet. So it's like T49 or whatever. Somebody can look it up and paste in the chat, and then we'll all laugh, because it's really stupid. I think my 10 got there. There you go. Anyway, those are the Roman numerals. And yeah, Roman numerals are dumb, but unfortunately that's the convention. And yeah, there's the name. Like, I don't even know how to alphabetize that. It's Kyle. I think that might be appropriate. All right. Anyway, suffice it to say, Elon Musk did not follow the systematic way to name children. So there's going to be a lot of confusion in that poor child's life. And that kid is definitely going to change his name when he's legally allowed to. Like, no doubt about it. As much as I am an advocate for, like, hey, if you are unique and you have something cool, stick with it. Like, that is very obviously, like, the parents just making fun of something. To me. Alright, so that covers how we name metals. So any metal name that we figure out, we're going to drop in the box. Now we got to talk about nonmetals. And I got to cough real quick, so give me a second. Fortunately, I was able to hit mute there. Alright. Now what we're going to do is we're going to talk about nonmetals. So whatever the name of our nonmetal is, we're going to put it in the box. But we're going to tear off the end of it and stick this on it, "ide." Now, what does "ide" mean? "Ide" signifies that you have an anion, and you only use "ide" if you are talking about an ion with a negative charge. So here are some sample names here that you might have seen. So, for instance, chlorine is the element off the periodic table, but we rip that part off and we write "ide" to indicate that there is a negative on the chlorine. Same thing for oxygen. Oxygen and oxide, nitrogen and nitride, fluorine and fluoride. You've probably heard all of these before, so you'll have a good intuitive sense on what the name should be. But in case you didn't, I don't reference what table or page that's on, apparently. That's unfortunate. This is in Chapter 4, though, so it'll be somewhere in the very start. I'm sure there is a table there at some point that just has all those stems, or maybe it's listed in the text itself. I know it's there, but I'm imagining what it says, so I feel like I've seen it. I just didn't reference it here, unfortunately. So now what we're going to do is we're going to actually start applying this. So first thing you're going to do is you're going to name the metal, then you're going to name the nonmetal with "ide." Remember the rules for putting down Roman numerals. Okay, so what would you call KBr? Well, K is potassium, so we'd write that down. And Br is bromine, but I would write it as bromide when I put "ide" on the end. So there you go. All right, next example. What is this? What is this? Type out the name of the metal, type out the name of the nonmetal in the chat, and give me a proper name for this. Because if I write it on the slide, I'm just going to overtype it with my slide text. Might as well make you guys do some of the work. So tell me what it is. And it's a race. And I say that even though somebody already finished. And yes, this is sodium oxide. Now, even though there are two sodiums here, there's nothing in our rule that says we care about number. And I'm going to highlight part of the statement because I mean this literally. When you are naming it, you're not going to care about the subscripts at all. But the subscripts can give you information that help you figure out what the charge is on one or the other thing. Usually, in the compounds that you're looking at, one of the pieces, either the cation or the anion, is going to be known. Most of the time, that will be the anion. For instance, you know what ion oxygen will always make. It'll always be O2-. But you might not know what ion chromium makes. And so you might have to do a bit of solving. We're going to see a few of those compounds in a little bit here. So next thing we're going to do is I'm going to take this pair of ions and I'm going to put them together. I'm going to put cobalt 2+ and chloride together. First I got to make a formula out of it, and then I need to give it a name. Type in the formula and the name that you should give it in the chat. And don't forget, what type of metal is cobalt when you are giving it a name? There you go. That looks good. I would call it... well, its formula would be CoCl2, because I need 2 of these guys. And I need 1 of these, so that the charges balance out. The name of that metal is cobalt 2, and the name of the chlorine with a minus on it is chloride. Alright, how about this one? What would I do with this one? What is the formula, and what is the name? And pardon me while I finish drinking my water here. Oh, be careful. Is Mn magnesium? Yeah, it's manganese. There you go. So the formula would be MnO, PQRST, UV, WXYZ. No, it would just be MnO. But yeah, be careful with manganese and magnesium because they're very similar. And then also beware of their alloy magnesium, which doesn't exist, by the way. Anyway, there's the name, manganese 2 oxide. Just some simple examples, so I'll give you a bunch more to try. This is page 1. On page 1, there are no transition metals, so all of these should be pretty straightforward. Go ahead and give the names of these compounds at the top here, and then on the bottom, I want you to turn the names backward into formulas, so that we have to go the other direction, too. So if you have 5 minutes to do this, we'll go over the answers, and then we'll give you page 2, which is just more of them. Okay? See you in a bit. How are you doing? Once you've got some of these, go ahead and type them in the chat window so I know where you're at. All right, one more minute to finish up. We'll go over the answers. All right, so yeah, that'll work. Okay. So let's name the metal here. So that's lithium. And then O is oxygen with ide on it is oxide. Be is beryllium. Cl is chlorine, so that will be chloride. Al is aluminum or aluminium. Either one is fine. O is oxygen or oxide. And then K is potassium. And I is iodide. All right, no problem there. Down here, we got to turn the names into ions first, which is a little more difficult. So we got to do strontium, and then bromide, and then I got to find the charges of these. Well, if you look at the periodic table and figure out their electron configurations and see how many they need to get a noble gas configuration, you should get this and this. And then putting them together is just a matter of, oh, I need 2 of these minuses to cancel out this 2 plus. So I need 2 of these and 1 of these. And there you go. We'll do a similar thing down here. So rubidium is Rb plus, nitride is N3 minus. Need 3 of these guys and 1 of these. And you get Rb3, N, or ribbon, which is not how you should call that. So it's not beryllium 2 because beryllium is in column 2. So it's just beryllium. Anything in column 1A, 2A, or aluminum does not need to have Roman numerals. Sodium sulfide, same thing. And magnesium iodide, same thing. All right, here's page 2. On the top there, I want you to give me the formula of the compound that you make out of that pair of ions, and then give it a name. And then down at the bottom, split those names into ions, and then if you want to write the formula, we'll write the formula for practice, but you could just do that as practice on your own. So go ahead and do these problems. Type them in the chat when you're ready. We'll go over the answers in just a second. How are you doing? Type your answers in the chat when you are ready. All right, let's go over the answers here. So we're going to put together these two ions here. So I have a +3 charge on my cobalt and a -1 on my bromine. So I'm going to need 3 of these guys and 1 of these to make the formula. And now that I know the ion, I can give it a name. It's cobalt, and the charge on it is +3, so I'm going to write Roman numerals 3. Bromide. I think Google thought that Cu was, I don't know, some sort of expletive. Let's see here. Titanium 4+ and oxygen 2-. I'm going to need 2 of these and 1 of these to get TiO2. Now, this is where the numbers get misleading. If you were going to name this based on just the formula, you want to know what the charge on this is, but you can't tell it from the numbers without breaking these apart. So, knowing that O is 2- and I have 2 of them, that's total 4- charge, so this titanium must be 4+. So that means titanium is titanium 4. And then that is oxide, because it's oxygen. Here I only need 1 of each. And so we get a curse. What a terrible night to have a curse. In other words, chromium 2 sulfide. All curses are chromium 2 sulfide, I guess. I don't know. Let your local witches know. And then finally, write the ions that make up the following molecules. So we got to write gold 1. Well, here's gold, and the 1 indicates that it has a charge of 1+. And we know what chloride is, and we can make that a formula. No problem. Sodium nitride, sodium is Na+. Nitride is, that's not where I meant to put that. N3-. Gonna need 3 of these and 1 of these. Barium oxide, barium is this, oxide is that. BaO. Finally, platinum 4 is PT4+. Fluoride is F-. And I need 4 of these and 1 of these, so the charges cancel out. And there you go. So that's naming ionic compounds. That's all you got to do. The trick here is going to be to make sure that you get the name right when you have all these different types of compounds mixed together. That's going to be the real trick. Alright, let's continue on to polyatomic stuff, which is exactly the same rules. However, you just drop in the name of the polyatomic ion whenever you see it. So if it's a cation, you put it in the metal box. If it's an anion, you put it in the non-metal box. Most of your polyatomic ions are going to be anions, so they're mostly going to fill in that second box there. I believe that Chapter 6 is the start of the polyatomic ions list. You are supposed to know those, but again, since it's an online class, I can't force you to know those. So, if you need to look them up, that's where they are. But we're going to do exactly the same thing as we did before. Name the metal, name the non-metal. How did I get platinum for? I got it because it says it right here. Oh, given an electron configuration, so it's a transition metal. So the reason that it comes out to be platinum 4, let me see if I can actually answer that. 1, 2, 3, 4, 5, 6, 7, 8. I don't have a good answer to that, unfortunately. It is just a state of platinum that exists. Alright, back over here, we're going to name the metal, name the non-metal, although the non-metal in this case is a polyatomic ion. This one's easy. And then we got to look up what MnO4 is. Well, potassium is an ion is K+. That means that this must be my polyatomic ion. And if you look that up in the table, you'll find permanganate is the name of it. And there's your name right there, potassium permanganate. What would this be? Oops. Spoilers. What would this be called if you didn't just see it flash on the screen? Well, if you look right here, name the metal, name the non-metal. This thing, whatever it is, must have a -1 charge, because again, the whole thing has to be neutral. And if you look this up, you'll find that it's called bisulfite. Alright, so here's some more practice. There's more on the other page, I guess. What I want you to do is look up the polyatomic ions on that list, or hopefully you've already memorized them. Type in the name of these compounds in the chat, and then down at the bottom, write a formula for the compounds that are shown. And then on the next page, we'll throw them all together with the metals and variable charges. So type these in the chat when you're ready. We'll go over the answers in just a second. I clicked on the wrong thing. There we go. Just a little longer to finish these up. We'll go over the answers. All right. So we have some mistakes in here, and it's mostly because I think people are unfamiliar with the polyatomic ions, but that's okay. Here's the ions that make up this. There's the name. And all we do is just name them. This is ammonium. This is sulfate. You're all set. I messed up. Erase. Boop. K plus is potassium. ClO3 with a minus charge is chlorate. Remember, you can sort of tell these just based on what the charge of the known ion is. So, for example, right here, I know that this is 2 plus, so this must be 2 minus. Barium carbonate. And then this one down here, lithium dichromate. Each lithium is +1, and dichromate is -2. Same thing down here. Take the names and then turn them into ions that you recognize. So we know that sodium is always Na+. Hydrogen carbonate is this guy from the list of polyatomic ions. So the formula must be this. This is actually known as baking soda, NaHCO3. Here's ammonium. Here's nitrite. Don't get nitrite mixed up with nitrate, because they're very similar. Nitrate has a 3, and nitrite has a 2. There's the formula. And then for potassium phosphate, potassium is always K+, and an ionic compound phosphate is PO4 3-. I need 3 of the potassiums to cancel out the 3- charge on the potassium, or on the phosphate. So there's my formula, K3PO4. All right, so there's your answers for those. Looks like most people got those correct at the bottom. But yeah, this does take a little bit of practice. So don't feel bad if you make mistakes, because, hey, that's what learning is about. I'm not testing you today. All right, here's the next set. Oops. I want you to turn these names into formulas. These involve some transition metals, so you'll have to have some Roman numerals, chicanery in there as well. So do these. I'll give you like 2 minutes to do it. We'll go over the answers, and I think it's time for a break after that. I'm looking at the slideshow. We actually have 2 more slides after this, and then we'll take a break. All right, let's go over the answers. And again, this is more of just a matter of, can you find the polyatomic ions on the list and match the names together. So calcium, we know sulfate is SO42-. There you go. Rubidium, we know Rb+. Hydroxide is this. Nickel 2 plus is nickel 2 right here. Cyanide is that. And ICN2. Gotta have parentheses around it, though, because otherwise it looks like the 2 is just attached to the end there. And then molybdenum 6 and phosphate. Would be something like that. Excuse me. Alright, so that's how we use polyatomic ions. Same as naming any other ionic compound. I do have more examples. This slide just tells you about, hey, here's how you use parentheses. Whenever you have more than one polyatomic ion, you got to put parentheses around it. Otherwise, if you don't, the intent is that it looks like, oh, I have 32 oxygens bound to this chlorine, and that's a little bit too much for any chlorine to have. So if you were doing calcium hydroxide here, we know, oh, okay, I'm going to need 2 of these things. But if I wrote this is my formula, now it looks like I have 2 hydrogens instead of 2 hydroxides. So the parentheses are necessary to fix that. For hydroxide, it's preferred that you do the O first, just because the convention is that if there's an H first, it's acidic, and that H on the hydroxide is not. I personally don't care, but Canvas will only accept it as OH when it's programmed in there. So, one last set of compounds for you to do. We'll do molecular compounds after the break, but do these 4 real quick, probably like a minute or 2. Alright, here are the answers real quickly. And again, we're just putting the pieces together like we have been all along. Two SO4, 3. And there you go. And the reason that we're doing them in these ways is because we want to make all of the charge on the ionic compound 0. So for this last one, if I did this times 2 and this times 3, now I have 6 positive and 6 negative. That'll give me a 0 total charge, and that's the ionic compound. All right, when we come back, we're going to do covalent compounds, which have a different formula to construct them. We'll hide that for now. Put the break timer up again. There is no timer, so hold on. All right, I will start the timer, and I'll see you in a little bit. Wow, 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 wow. Oh, I'm not sure if it's possible to get exactly 10 on here, just how the frames work. But hey, that's close enough, right? Boop. Boop. Did I actually turn this off? Yeah, I did, okay. Alright. Sorry, big yawn there all of a sudden. Let's name molecular compounds. These are going to follow a totally different algorithm. And the subtlety in this is that it seems like it's similar, but it's really not. So you're going to notice here that we name the first element and then we name the second element with "ide." But we have these like numeric boxes here. We're going to be putting prefixes in those boxes to indicate the number of things that there are. Now, what element goes first and what element goes second? We're going to arrange the elements by electronegativity. The element that is more positive or has a lower electronegativity is listed first. The element that has a higher electronegativity is listed second. Now, there are some exceptions, and those exceptions generally occur with hydrogen, because hydrogen's weird about where it bonds and what it bonds to. But for the most part, you will not need to worry about that. Oh man, no, I'm just tired all of a sudden, excuse me. You won't have to worry about that because I will give you the elements in the proper order. If you were typing them into Canvas, you will definitely have to make sure that you are putting the more positive one first and the more negative one second. If it's ionic, always put the positive element first. If it's covalent, follow these rules. Now, we only use numeric prefixes, that is these number boxes right here, so this guy and this guy. We only use those for covalent compounds. So it's very important to note that you're never going to start putting these prefixes on things that are not covalent. That means no ionic compound should ever use these prefixes. So don't ever say disodium. Like, don't do that. They'll immediately just be wrong. Oh, my sinuses are going crazy. Allergies or something, I don't know. Here are the prefixes from your textbook. When you are applying these prefixes, you just take this name right there and you put it right in the box. You know, you'll notice where it says sometimes omitted. For mono, if there's only one of the first element, you don't put mono. You only use mono on the second element. So CO would be carbon monoxide. And not monocarbon monoxide. CO2 is carbon dioxide instead of monocarbon dioxide. We don't put the one if there's only one of the first element. Now, sometimes when you are spelling out words, you get these kind of obnoxious letter combinations. So if you see anything that looks like this, where you get an A from the prefix and then the first letter is O from oxide or something like that, or if you get a double O, we drop the letter on the prefix. Okay, so that would be, if I had, like, say, pentaoxide, I would get rid of this A and just do pentoxide. If I had monooxide, or monooxide, we would just get rid of one of those O's, and then there it is, monoxide. Those are the only pairs of vowels that we modify spelling for. There are other pairs of vowels that will occur, so like double I or IO, but those aren't changed. So only AO and OO are changed, for whatever reason. Other than that, this is just like naming ionic compounds. We're going to name the second element with "ide," the first element as is, and then you put in these prefixes. So let's name some of these. Oh, and then, of course, since there are no charges on covalent compounds, never, ever, ever use Roman numerals in covalent compounds. Okay? So if you write carbon 4 oxide, I'm immediately just going to be like, oops, don't know how to name covalent compounds, and that will get marked wrong. Okay? So be careful. So let's start naming some of these things. We're going to follow the naming scheme of name the first element and then name the second element with "ide," and then we'll put the prefixes in there. So this is nitrogen. This is oxide. And now I just got to deal with the numbers. 2 is di, and 5 is penta. But if I had an AO, I would drop off the A and become pentoxide. How about this next one? We got S, which is sulfur. We got O, which is oxide. There's only one of them, so I don't put mono because it's the first element. And then I put di for 2. This is sulfur dioxide. All right. What would I call this? There you go. This is just water. Nope, we can't call it water anymore. Sorry. Water is a common name. We need to actually call it what it is. So this is hydrogen. This is oxide. There's 2 of these and 1 of these. And because it's the second element, we do include mono. I'm going to move that a little closer so it doesn't look like I'm intending for there to be a space there. And there you go. So water is actually known as dihydrogen monoxide, which makes this next page a little interesting. This is actually a thing. I think that this was just done as a joke, but in an era where anything can be posted online, and if you do no research, people will believe it. And I'm actually going to show you this webpage in just a second. Actually, let me just get that ready right now here. And you can actually read about this. I am going to put a warning as a preface. Alright, so this is the site that I am referring to. This is dhmo.org, which is totally bogus. And I believe that it is put up as a joke. But if you were not aware that this is how chemicals are named, you could seriously find this website to be dangerous. And case in point, I'm going to give you the list of symptoms and causes that this compound, this supposed terrible thing, has done to frame the narrative in a very specific way. And then I'm going to say one country proposed this in the Senate on April Fool's Day, and everybody had a good laugh. And then another country did this as an April Fool's segment on the radio, and there was mass panic, and the radio station shut down completely within an hour. Okay? So, here were the things that were posted on both of these about dihydrogen monoxide. So, it has a common name called hydroxyl acid, and it's also the major component of acid rain. I don't know if you knew that. Just in case you weren't aware. Major component of acid rain, yeah. It contributes to the greenhouse effect. In fact, this is a more serious greenhouse gas than CO2. It is very capable of reflecting heat and absorbing heat. If you come into contact with it, you can be burned severely. If you breathe it, you will die. Dihydrogen monoxide is that bad. Do not inhale. It contributes to erosion of landscape. So pretty much everywhere in the entire world has been just deteriorating because of this compound since pre-civilization, and it accelerates corrosion and rusting of many metals out there. There's no metal that resists reactivity from it. And it can cause electrical failure. It can cause decreased effectiveness of brakes. You might try and use your brakes on a day where there's lots of dihydrogen monoxide contamination, and you won't be able to stop, and that could be really dangerous. Every single person who has cancer has this in them. Somewhere in their body, dihydrogen monoxide. And despite all of this danger, we still use this terrible, terrible thing. We use it in industry as a coolant. We use it as a solvent. It's used in nuclear power. We use it to make styrofoam. We use it to put out fires. We use it in animal research. It's even in your food. Even if you wash your produce, it's still contaminated by dihydrogen monoxide. And it's used in junk. And if you saw all of this information and you didn't know what this compound is, you might think, oh my goodness, this is terrible. What is going on? But what is this compound? What is this mystery substance? Pardon my French, but it's fucking water. So, going back to our question at the beginning, where we talked about this compound and about misinformation, and how important it is for you to have a basic understanding of what it is that's being talked about. The first country was Australia. The second country was America, when I was referring to those two things. Who do you think, between Australia and America, was the we put this in the Senate and everybody voted on it and was like, that's silly, to raise chemistry awareness? And which country had mass panic and shut down a radio station, and all of the people who were part of this got put on suspension? Can you guess what country it might be? I'll give you a hint. Kind of parallels current events. Yeah, it does. So, what's the takeaway from this whole thing is that if you are presented with information, do the best that you can to verify it, because people are going to try and mislead you. And there's a lot of this going on right now on the media, on the news. Anything that you see on the news is pretty suspect, I would say, because people are just trying to cover up for what's going on. They want to maintain the status quo. And that's not okay. So if you are questioning something that you read or hear, and you should do this for everything that you can, try and follow up on it, find more sources, read up about information, and make sure that you aren't getting sucked into a propaganda trap, because people are preying on your lack of knowledge. Because, again, it's fucking water. And interestingly, if you go to the DHMO website, let me see if this is the right window capture. Yeah, here we go. Can I make this bigger? Yeah, there we go. So specifically what I'm trying to capture is, I don't know if it will show. It almost doesn't. So what I want to do is, let's see here. I don't know what I was looking for Ganon for. I'm probably trying to... Oh, I was trying to find that track from the Zelda. They took down the website on YouTube that I was using for music the other day, and I was really upset. So I have to find new music to play during our interstitial things. I'm going to type in water, and you can probably hear... Oh, you can't hear it. Let me do this. So, I'm going to type in the word water, and I got to T-E-R. Oh, I didn't actually turn up the sound here. I don't know if you can... There you go. You can hear that ding, 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 because what that means is that as I type in the letters for the word water, it found no hits. The word water does not show up on this website at all. In fact, if I go to the dihydrogen monoxide FAQ, here's that list of things that I took this from. So you could see that these are all the things that showed up on that. And if I type in, find the word water, W-A-T-E-R, there is no mention of that word on here. So yeah, literacy is extremely important. Make sure that you don't fall into the trap. All right. Thanks for coming to my TED Talk. Here are some molecular compounds. What I want you to do is write the name of the first four and then turn the bottom ones into a formula. This process is actually quite easy, so I'm going to give you 3 minutes to do that. I got to go fill my water anyway, and I'll be right back. We'll go over the answers. All right, I'm back. So let's name these compounds. I don't know why that happened, but I have the wrong pen selected too. There we go. So there's the element names. I put "ide" on the second one. Then I'll go back and fill in the numbers. So 2 is di for nitrogen. Mono for oxygen. We'll chop off the extra O. Get dinitrogen monoxide. There you go. This is probably the safest way to do this. Eventually you get to the point where you just do it on your own. Be really careful with spelling permutations. Fluoride, for example, is UO and not OU. If you do OU, you get flouride. The way that I will set up the spelling tests on Canvas is that I will try and give you a number of permutations that you can accidentally do. So if you accidentally superimpose 2 letters, it should be fine. Or if you add an extra letter somewhere, it should be okay. But that's not going to catch every instance. So just be very careful when you're typing this in and I ask you, like, what is the formula for P4010? Because you want to type exactly that word for the first thing. And if you accidentally put an O right here, then Canvas would mark it wrong unless I give you what's called Levenshtein distance or something like that. So 10 is deca, but because it's oxide, we're going to get rid of that A. And then finally, this part's really easy. So di is 2 and boron is B, so there you go. And then tri is 3 and oxygen is O, so we're all set. And you could just quickly whip these guys into shape. That doesn't really look like a fluorine. There we go. There you go. That's covalent compounds. Covalent compounds are really easy. Relatively speaking. The trick to doing these is that you don't get it mixed up with the ionic rules. Alright, the last bit of naming that we're going to do today, we're going to do acids. For acids, there are 3 unique naming schemes, and we got to know what they are based on the anion that we're involved with. So the first thing we want to talk about acids is what are acids. An acid is anything that contains H+ in it and some other anion. What that means is that when we put it in water and it splits off, H+ fills the solution. Anything that does that is an acid. Water does this, and it's technically an acid. Turns out water is the definition of the weakest acid. We'll talk about that in 163. But anything that also does this to a greater extent than water will be named an acid. Now, when we create acids, there will always be enough H pluses to neutralize the charge on the anion. So, for instance, if I have HCl here, Cl has a -1 charge, so I need 1 H plus to counteract that. Phosphate has a 3- charge, so I need 3 pluses to counteract that. And this will always be true. So when you look at the polyatomic ion on the list of polyatomic ions that we would be using, you can make acids out of any of them by putting enough H's to cancel out the minus charge. The one you can't make an acid out of is ammonium because it's positive. You can't put H pluses on something that's also positive. In fact, that has already been done, which is how you got ammonium. Now, there are 3 different rules to name acids, and the first one actually has 2 different states here. Now, the first type of acid we're going to use is binary acid. So this is something like HCl, HBr, HF, H2S. There's 2 different elements in there. With binary acids, you have to check to see whether you're looking at something in the gaseous state or the aqueous state. Okay. Gaseous binary acids are named hydrogen whatever-ide, like you would name it as a covalent compound. But if the acid is aqueous, we use a different procedure. We say hydro plus whatever the stem of the ion is plus ic acid. Only the stuff that's in blue is going to be modified here. So this guy and this guy will be modified, but everything else stays fixed. So you have to use these terms. So for example, if I had, say, HCl as a gas, what I would call that as a gas is hydrogen, and then chlorine with ide on it, which is chloride. So hydrogen chloride would be HCl as a gas. But HCl in aqueous solution would be hydro. The stem for Cl is chlor, because that's the part that we keep when we get rid of ide. And then we add ic acid to it. So HCl as an aqueous solution would be hydrochloric acid. Now, an interesting thing is that hydrocyanic acid also follows this because cyanide ends in ide. It turns out that your textbook doesn't mention this, but the rule for this acid right here is if the ion that you're working with ends in ide, you use this rule. So that'd be chloride, sulfide, nitride, etc. They all end in ide, you follow this rule, provided they're aqueous acids. Now, sulfuric acid is something different. And so H2S in the aqueous state will have a different name. In fact, H2S is not very acidic at all. But H2S is a gas, which is actually how you see it, is hydrogen sulfide. But yeah, we're gonna see sulfuric acid in a second here. So if I wanted to name these, all the gases would just be hydrogen whatever. Here's hydrogen fluoride. And again, U before O here. And then these are aqueous, so we got to go hydro whatever-ic acid. So there's that. That doesn't look like a U. There's fluoric acid. There you go. Alright, that's how you name acids. For the rest of the acids that we're going to encounter, they have oxygen in them, so they're called oxyacids. And there are two different rules for this, and they are going to depend on what the ion ends with in its name. So that could be either ate or ite. And I realize I'm a little off the screen there. So if we have something that ends in ate, we're going to use this nomenclature scheme. So whatever your polyatomic ion has with its name, you get rid of the ate and replace it with this. So this would be an example of, here's sulfate, which is this ion right here. I get rid of the ate, and I write ic acid. And for sulfur, we actually have to add in this extra little thing right here. That's really sloppy, so I'll do the examples. We'll come back to that in a second. But you can see where this is going. So if I have ite, I do the same thing, but I end it with us acid instead. So I'm going to take off ate and put ic acid, or I'm going to take off ite and put us acid. I'll give you a second to write that down, and then we'll go over the examples. And there are two spelling exceptions. One of them I just showed you, which was sulfur, because you get sulf, which apparently sounds stupid, so they make it sulfur. The other one is phosp, for phosphate. That becomes phosphor. So let's do some examples here. So the first thing we need to do is we need to identify what this is. We know that this is H+, so that the rest of this must have a charge of minus. And so now you need to look up what polyatomic ion that is. And if you do, you'll find this. It's acetate. So now what I need to do is I need to chop off this part. And follow the acid rule. It ended in ate, so I'm going to replace that with ic acid. This is called acetic acid. Or vinegar. You've probably heard of vinegar before, I'm sure. Alright, let's do another one. Gotta clear the screen for that, though. Give the name for this. Again, we have H+, which means that this other thing must be NO2 with a -1 charge. If I go look that up, it's called nitrate. I'm going to get rid of the ite and replace it with us acid. So this becomes nitrous acid. All right, one more. Or two more, actually, because I'm going to have some examples here. So if you get these as your stems, sulf... Oops, I went a little too far with the pen there. Actually, let me just do this. So if this is your stem, sulf or phos, from sulfate or phosphate or whatever, then what we end up doing is we actually end up tacking on a few extra letters to make it sound better. So keep that in mind when you see these two examples here. So I got H2SO3 and H3PO4. So I got H plus, I got two of those, which means that this must be 2 minus. SO3, 2 minus is sulfite. So I'm going to get rid of the ite part. There it goes. And type in us acid, but because it's sulfur, I got to add extra letters so that it doesn't sound silly. For phosphate, same thing. I got 3 of these, so that means that this must be 3 minus. That's phosphate. We're going to chop off some of those letters from the 8 and put ic acid on there. But because it's phosphorus, we're going to do that first before we put ic acid on there. There you go. So we have sulfurous acid and phosphoric acid. You get the gist of it. Clear all my ink. There we go. All right, so here are a bunch of acids for you to try. What I want you to do is name the ones on the top, and then write the formula of the ones on the bottom. You will have to look at your polyatomic ions list for this if you haven't memorized them. Give you 5 minutes to do it. See you in a bit. We'll go over the answers then. How are we doing? Type those answers in the chat when you got them. Alright, let's go over the answers because we're almost out of time for the day. So this right here is perchlorate, which means that this becomes perchloric acid. We have H-bro. This is hypobromite. Hypobromite. We get rid of the ite and it becomes us acid. This is dichromate. Get rid of the H and call it ic acid. Dichromic acid. We talked about cyanide and how cyanide ending in ide follows the ide rule, which would be hydrocyanic acid. PO3, 3 minus is phosphate. So there's the ite gone. We add the or to make it sound better. Phosphorus acid, which I know sounds really weird because isn't it just called phosphorus? Well, phosphorus, the element, doesn't have this O in it. So again, be careful with spelling. Excuse me. And then you got to turn these guys from their name into an acid, and that's a little bit more difficult. We're going to see that there's an ick here, so that means that must be an 8, which is sulfate. And I need 2 H pluses to, oops. To neutralize the 2 minus. There's the formula. I got an ick on the end, so this must be nitrate, which is that. There you go. Ick again, so this is chromate, which we'll do over here. Chromate is CrO4 2 minus. So I must need 2 H pluses to cancel it out. There's the chromic acid. Hypochlorous acid, so this has us, which means it must be hypochlorite, which is ClO minus. There you go. And then finally, this looks like it's periodic acid, but it's actually got this ick here, which means that it should be replaced with an 8. This is periodate, which is this. There's the acid. Alright, I believe that's all the time we have today. Yeah, it's already 2:50? Yeah, 2:52. So when we come back, we're going to do, on Tuesday, the easiest thing in the class, which is Lewis symbols. And then we're going to quickly make it more difficult by drawing all the Lewis structures ever. And hopefully, we will be able to get through Lewis symbols, formal charges, and a bunch of this stuff, because I'm gonna run out of time. We're actually a little bit behind here, given that I don't get as many days as I thought. The last day of class is actually the final exam. So I will try and do what I can to get us on track. There will be plenty for me to test you on, don't worry, because Chapter 3 is very long. And we still have a whole week of lecture and content to cover, so we'll probably get through almost all of this. I want to thank everyone for showing up to lecture today. Have a wonderful weekend. Make sure that you are keeping on top of the material and on top of the due dates. Get that worksheet in tonight. Work on the Chapter 3 quiz when you can. Stay safe, stay healthy, stay at home.